Hello everyone, welcome to the M2L31 series Level 1 training course. In this video, we're going to introduce a low power ADC example. The main focus is to show how we can use auto operation mode to let the ADC automatically sample voltage data by hardware in low power mode. With this approach, even when the system enters a low power state, the ADC can keep running continuously without needing the CPU to wake up. This makes it a very practical solution for low power sensing applications, where saving energy is critical. You can download the example program from the link in the video description below. Once you've downloaded it, just extract the files and open the project in the Kyle development environment following the provided path. This example runs on the NuMicro M2L31 SG development board, and it builds directly on the concept we just introduced. In this demo, we configure PB2, which is pin 5, as low power ADC 0 channel 2. This pin is used to measure the voltage at different test points on the development board. Once the voltage is sampled by the low power ADC, the conversion results are then sent out through low power UART and displayed on the terminal. So you can clearly see the measured voltage values, even while the system is operating in low power mode. If you want to connect your computer to the development board to monitor the output messages, make sure to enable the virtual COM port on the right side of the board. Specifically, turn on the TXD and RXD switches. As shown in the diagram, just slide both switches to the right. This way, your computer will be able to properly receive the messages sent from the development board. Next, let's walk through the overall flow of this example program. First, we use the low power timer to trigger the low power ADC every 500 milliseconds. The ADC conversion results are then sequentially stored in the low power SRAM through low power PDMA channel 0. Once the PDMA accumulates 10 data points, it generates a wake-up signal to bring the CPU back to life. Then, using UART, all 10 ADC values are displayed at once. After displaying, the CPU goes back into power down mode. This approach greatly reduces the number of CPU wake-ups, effectively lowering the overall average power consumption. Next, we can take a look at how the different peripherals are connected using the bus matrix. In the system, the CPU acts as a master, and through the bus matrix, it can read from and write to the various modules inside the low power domain. Within the low power domain, the low power PDMA also acts as a master. It can directly read the conversion results from the low power ADC and then write those results into the low power SRAM. Now, let's take a look at the program itself. From the main function, you can see the overall structure of the program. In this low power ADC example, we actually use only a few key features: the tick timer, the low power ADC, and the low power PDMA. These modules work together to achieve automatic operation in low power mode. As for the initial system setup, like the minimum current init, system init, and UART init functions, you can refer to the low power timer sample code video for detailed explanations. In this example, let's start by looking at the ADC initialization process. First, we configure PB2 as low power ADC channel 2, and at the same time, we disable the digital input path to avoid unnecessary power consumption. Next, we select low power ADC 0 as the main controller and enable it. Then, we turn on auto operation mode and set the trigger source to timer 0. Finally, we disable the ADC interrupts. This is because the entire conversion and data transfer process is handled automatically by the low power PDMA without any CPU involvement. This is a key part of achieving low power operation. Next, let's look at the timer configuration. We set the tick timer to periodic mode, counting every 500 milliseconds. When the count completes, it automatically triggers the low power PDMA to start transferring data. Again, this whole process happens without any CPU involvement. Next, let's go over the low power PDMA configuration. Here, we set the transfer width to 32 bits, with a total of 10 data points per transfer. The data moves from the Low Power ADC's data register all the way into the source array stored in Low Power SRAM. Once everything is set up, we can flash the program and see the demo in action. Now you can open the Kyle project file from the path we mentioned earlier. Next, click Build to compile the project. Once the compilation is complete, connect the development board to your PC via the debugger's USB port. Then, click Download to flash the program onto the board. Here, let's take measuring the VDD output as an example. Basically, we calculate the VDD voltage using the values from the ADC. For the test setup, we simply connect PB5 to the VDD pin at the top left corner using a DuPont wire. Next, we can open a serial communication tool and remember to turn on the TX switch on the development board, like we mentioned earlier, so we can see the messages sent out through the UART. At this point, you'll see the ADC conversion results being output to your PC via the UART. The result shows as 0xFFF in hexadecimal, which converts to 4095 in decimal. You can also try measuring the LDO cap or the VSS pins. After taking the measurements, you can use a multimeter to measure the actual voltage and verify whether the ADC conversion results are correct. Here, you should note that the pin assignments might differ depending on which development board you're using. If you need to check the exact pin locations and their functions, you can refer to the Pin Configure tool or the datasheet. Finally, we measured the system's current consumption. From the results, you can see that since the CPU doesn't need to be woken up frequently in this application scenario, the system can stay in power down mode most of the time. The benefit here is that the CPU only wakes up when it really needs to handle a task, and otherwise stays in low power mode to save energy. As a result, the overall average current consumption can drop to around 25 microamps. This is especially important for battery-powered applications, as it can significantly extend the system's operating time. By looking at the current waveform and correlating it with the program's behavior, you can see that the peaks indicate moments when the CPU is woken up because the PDMA has finished transferring the ADC values. You can adjust the wake-up conditions based on your own requirements, which allows the system to stay in sleep mode longer and achieve even greater power savings. That wraps up our introduction to the Low Power ADC sample code in this training session. Thank you for watching, and if you'd like to learn more, please feel free to reach out to us.